Assalamu alaikum. This project demonstrates the design and the working of a very small 8-bit computer SAP-1, simple as possible one in Logisim Evolution. SAP-1 is widely used in education because it shows in the simplest possible way how a CPU fetches the instruction from memory and decodes them and executes them step by step. Our build goes one step further. We implemented a hardware control sequencer so the processor can run automatically, and we extended the instruction set with shift rotate operation. I am Tastava Islam here showing you a demo where you will see the full architecture, how we load the program in manual loader and how the same program run end-to-end automatic mode using the control sequencer. At first, I'm showing you the full architecture in both manual mode and the automatic mode. This is the architecture of the manual mode and this is the architecture for the automatic mode. Now, before moving to the automatic execution, I will show the architectural components that are required for SAP-1 implementation in manual mode. Here, I will explain you their purpose one by one. First of all, we go in the register, general purpose register. These hold data temporarily and are used for arithmetic and logic operation. Now, second one is ALU, which is called arithmetic logic unit, which is used for the arithmetic operation like addition, subtraction using the data from the register. Next, the decoder. It's an 4 cross 16 decoder which converts a 4-bit opcode into one of the 16 unique signals to identify instruction. Now come to the SRAM cell. This is an SRAM cell which is a basic memory storage element where a single bit of data is stored. This is the full architecture of an SRAM where the complete memory unit is here where the instruction and the data are stored for program execution. Now come to the instruction register. In the instruction register, we use the instruction register to store the current instruction fetched from the memory and separate the opcode and the operand. Now come to the ring counter. This is a ring counter which generates the timing signals like T1, T2, T4, T5, T6 stages to control the step-by-step execution of instruction. Now, the INS decoder. This is an instruction decoder which decodes the opcode from the instruction register and activates the corresponding instruction line. Finally, there is a ring counter also. It's a ring counter and this is a program counter. Finally, the control sequencer one. The control sequencer unit combines the timing signal and decoded instruction to automatically control the fetch, decode, and execute cycle. Now we will see the implementation. First, we go in the main circuit of manual control sequencer part. If you see, for if you want to store the first, we will prepare the RAM by storing the required instruction and data. For this, we will have to enable control sequencer first, then the debug pin, then also give a pulse in PC reset. Now, for the debug pin, we have to first decide the address, the memory address. For memory address 0, we have to give a pulse in marine manual enable and then a clock pulse. Then stop all the pulses. The address is selected. For this, in our instruction, for the addition, we have to load the data in 12 number of 12 number LD12. It means 12 number in RAM. So first in 00 address, we have to give the instruction. This is our instruction, which is 000 111. 0. So for we will give 000 1 1 1. This is the instruction set. If you see the instruction set, that is here, that is 0001110 for 12 number address. The instruction is given here. That is 11100. Okay. Now for this we have to give SRAM write and clock pulse. Then stop the pulse in SRAM read. So you can see the change here. The address we have given, the instruction we have given in address 00 is stored here. You can see in the RAM. Now the second one for the second one address we have to set the address first. That is 01. Marine. Then give a clock pulse. Stop the marine. The second address is selected. Now for second address, if you see in the instruction table, the second address is 00101101. Okay, now we have to write this 00101101. Now SRAM write clock pulse and S stop the clock pulse in SRAM. So you can see here the data is stored in address 2. Now we have to select the address number 3, that is 10. Now marine, give a clock pulse. The address has been selected. For that we are doing the addition part. So in addition we have to give the addition instruction in number 3 number of address. So addition instruction is 001140. Then we give 0011 and others reference 0. Now SRAM write manual and clock. If you can see, the third number address is filled with the addition instruction. Now we have to select the fourth number of address and the fourth number of address here for store. In store we have to give this. So the store value is 0101 and 4 ones. Because we are not using the jump, that's why we giving the addition in number 3 number of address and store in 4 number of address and halt in 5 number of address. Okay, we will check another time. 0101 and 4 ones and 4 ones. Now we have to give the SRAM write manual. Sorry, one SRAM write and give a clock pulse. Here the value is stored in address 4. Now we have to select the next address. First we have to stop the pulses here. Now first we select the fourth number of address, marine and clock pulse. So the address has been selected. In this we have to give the instruction for halt. The halt instruction are 4140. That's 41 and 4 zeros. You have to be careful when you are giving the manual inputs. Now SRAM write manual and give a clock pulse. If you see here. Now we have to give the data for 12 and 13 number address. First we have to select the 13 12 and 13 number address. There is it's 12 marine manual. Give a clock pulse. Now for the instruction set, I have used the decimal number 51, which binary is, which hex number is 33, which binary is 00110011. We have to give the data 0011 and 0011. SRAM right clock pulse. If you see here, now I have to choose the 30 number address, that is 1101. Marine, give a clock pulse. Stop the pulse here. The address 13 is selected. In 13, we have to give the decimal value 25, which binary is 000111101. That's 000111001. This is the address. SRAM write manual. Give a clock pulse. So if you can see, my debug is done for addition. Now I will stop the pulses here in debug. Now I have to give the clock pulses. If you see in my ring counter, there are 6 time states. It means for one instruction, it will go through a 6 time steps. So if you see here, there are my 5 instructions. Like first the load A, second load B, third addition, fourth store, and fifth halt. For this, I have to, per instruction, I have to give a clock pulse of number 6. So for 5 instruction, I have to give 30 clock pulses. First, I will give the 6 clock pulses. I have done some the mistake. I think I didn't give the PC reset. It's an important thing. After that, you have to give the 6 pulses so that it will change in here. Here, have you seen this? This is the A, the register, the 13 value load A is stored here. Now I will give the pulses for load B. Keep I in here. Here, the load B is also stored in register B. Here at the 13 number address. Now the addition will be stored in here. Did you see? The addition of A and B is stored in register A. Now after the second half, after this next pulses, the value will store in RAM 15. Just keep an eye here, keep your eye here. Here, the value is stored. After I have to give another 6 pulses to hold. Here, the program is ended. This is the addition. So the addition is done manually. Now I will show you the same instruction has been done in automatic zone. In the automatic, we have to first go to the automatic control sequencer, automatic architecture of SAP-1. Here I have just uploaded some uh, components. The register GP will be the same, but in I have changed in this. Here in instruction decoder instruction tab, I have just added some more instruction like edit, subtraction, store, jump, shift left, shift right, rotate left, rotate right. In here, I have used an automatic PC loader. It's a built-in counter which will count automatically. Now, I will go to the main circuit. Okay, I will show you again in my control sequencer, my updated control sequencer where I have used jump, the shift rotate, and the shift rate, shift out, shift different rotate. This now come to the main circuit. In the main circuit, first we have to see this. This is an automatic RAM loader. By this, it will use by this if we when we give the hex file here, then it automatically load in the RAM, ROM to RAM. For this, we have to give the hex file first. For that, if we go the addition hex file here, there is a question how I make this hex file. For this, I have used a SAP compiler. It's a compiler which I used for the addition, subtraction, jump, shift, rotate, all the values. Where the code or the instruction given here, and if I give the assemble hex, then it will assemble a hex file. Now I will show you the how it will done in automatic set. First we have to give pulse in the debug pin. Then of course PC reset is an important thing. Before doing any instruction, we have to give a PC reset. Now giving the clock pulses. Look at the loader counter value here. Here the value are counted. The 16 bits will be counted here. Okay. Now done with the loader. If you see in the RAM, you can see the values are loaded from the ROM. Now I will just stop the pulse here in debug pin. Now I will do the PC reset and but I will give clock pulses. The fetch, decode, execute will automatically happen. You will see the register A value and the register B value. After that, you will see in the store value, which we will get in the automatic mode. Okay, giving clock pulses here. The register A value is stored, register B value is also stored. After counting, if you see after counting, oh, after counting 6 here, you can see the value is stored. And this is the exactly same value which we got in the manual part. This is an automated execution. There, I didn't need to do anything manually. Like in the first thing you have seen in that I have done the debugging and marine and I will hold the RAM part. After that, I have used control sequencer. Here, I have a built-in ROM which will turn into all the values in the RAM. Then the addition part. Now I will show you another instruction that I have done. Now I will try a next for which is jump. I will open the jump hex file which I have just made by the compiler. Okay, save. Okay, it has been saved. Okay, done. Now I will just do as the simple I have done for addition. First give a pulse in debug please. PC reset and the data. I have to load the data in RAM. So if you see the loader counter value, okay. Now I will stop the debug pin. I will have to do the PC reset. If you see a change, there will be when you have to take care, you have to give an I here. When I am giving pulses, see the counter value 1, 2, and then it's jumped into 5 because I have given J5. If you see in my instruction, jump 5. Program counter will be jumping to instruction number 5. So it just dumped it in counter value 5. So this is my jump execution, and I will show you another execution. For my next, I have done shift rotate, shift left, shift right, shift rotate also. So I will do the whole execution. I have done different also, but I will do the whole execution together to show you the whole thing. Here, this is my hex file. Now, first I have to debug my data, PC reset, and give a clock pulse. So if you see, the data are stored here. Then I will stop the debug pin, and then I'm just doing a little bit zoom in. Without that you can't see what's happening in RAM. So after giving the clock pulses, I have given the number of 90. Okay, we have to give the PC reset value. For 90, there will be a shift rotate part. Here I will give the clock pulses. If you see, there will be changes in RAM address 15, 14, 13, and 12. That is shift left, shift right, rotate left, and rotate right. It's all happening in the most significant bit and the least significant bit because I have given the instruction in rotation by 1 bit. So here you can see, I will make a zoom here. Mhm. Mhm. Here you can see the changes. This is shifted left, right, rotate left, and here. These are the changes. These are the changes I have done in my control automatic control sequencer. I have updated by shift rotate all the parts. For this I have used this automatic shifter. If you see here, I have used 4 shifter for doing the shift rotate part. There are many changes can be done by updating a chip design by SAP compiler. It's just a simple SAP-1 SAP-1. I have just tried a simple instruction like jump and shift rotate. It can be also we can also add it there the logic circuits like and or not. There are many things we can do. So I have worked for addition, subtraction, jump, shift and rotate part. There are many things can be done. So that's all from my side. Thank you everyone for listening my video for so long. Thank you so much.